Oh. Is that good? Actually, is that best? You got reading lamps? Okay. That's best at the back too. No sleep sitting. So, well, let's get with our usual edutainment before we get going with other things. You know, we've been talking about fluid pressures on structures. And so we'll do some more work on, so what we've covered so far is forces on plane structures, flat. What we haven't done are forces on curved structures. And of course the other thing that fluid pressures play into are things like buoyancy. So we'll talk also about buoyancy. And so this is a well-known example, the Costa Concordia from a couple of years ago, I guess, but it was only salvaged maybe this summer. This is the smart captain who's wining and dining in his stateroom within the, in the ship, while he wanted to do a drive-by or a sail-by of a local island for show or whatever, and went a bit too close. Got a hole gouged in the side of the ship, and the consequences were, I mean, very lucky. I think maybe 40 people died, but he was able to limp it close enough to the shore so that actually when it tried to capsize, it was arrested. And so a whole bunch of other unfortunate events, like him getting off the boat before everyone else, among other parts of the news. So you'll probably remember this. This is certainly in your adult and cognizant lifetime. The salvage operation, I think, is quite clever. So it sits, gives a pretty graphic picture of where it sits. They build some caissons around it. They overweight the one caisson here by filling it up with water to provide a weight. To rotate it, they pull down on this to be able to right it on this special platform. And then once they have it righted and stabilized, then they pump out add another caisson and pump out the water out of these tanks. And Bob's your uncle, I guess I would say. It's a strange expression, but all of a sudden it floats and then you take it off, not to retrofit, but I presume it goes to salvage. And so we'll talk about, everything we've talked about of forces on structures is the same as contributes, for instance, to buoyancy, including breaching of experimental submarines, I guess, in this particular case. I think more dramatic breaching is included in other examples. I don't know if the sound is overplaying these. Hopefully not. No, it's not. Good. So, not maybe in your lifetime, the Kursk, Russian submarine on maneuvers in the Barents Sea in the northern part of Russia, in the Arctic Sea, I guess. On maneuvers and had an explosion on board, went to the bottom, and they tried for a week to try and rescue people. It wasn't very deep, it was a few hundred feet. So they tried to rescue people with diving bells, but to no avail. There were no survivors ultimately. And of course, the dramatic footage of submarines breaching, I guess, either in emergency events to get to the surface, or I think in some cases for show. And specifically for show in this one particular case, one event, the unfortunate event off the Hawaiian Islands, also maybe, certainly it was before Gore's, Al Gore's, I think it was before his presidential bid, which would have been 2000, was the emergency breaching of a submarine, the Greenville, which happened, incredibly unfortunately, in a huge ocean with usually nothing much in it, came up above a Japanese training ship, fisherman training ship. So high school students on this thing learning how to be fishermen, big part of the Japanese economy. And unfortunately, this ship, which I think had Tipper Gore on board as a dignitary, Al Gore's then wife, Al Gore of the unpleasant truth or inconvenient truth fame and Nobel Peace Prize winner for that, came up underneath this ship and it sank with all hands on board. And so a number of people were lost, unfortunately, including, I think, maybe nine people died, including 4 high school kids from Ehime in Japan. And so very sad events. And maybe not so, but also relevant, I guess, to the issue of buoyancy are things like tsunamis. And so the 1929 Grand Banks earthquake. The Grand Banks is the area off the eastern coast of Canada. This, by the way, is the Bay of Fundy, where my pen is, my pointer is. So the Bay of Fundy is this little thing in here, which has this resonance to give the highest tides in the world. But an earthquake set off an unstable piece of the Grand Banks. The Grand Banks is basically sediment that's been scraped off the North American continent by the ice sheets and sits underwater, and was kind of a high point in the ocean that was a breeding ground for cod. And so fishing vessels from all of Western Europe and all of North America, for that matter, used to fish here before the cod stocks were depleted. But in 1929 there was an earthquake. The earthquake triggered this unstable mass, and it flowed down the continental shelf and triggered a tsunami. Knowledge of this landslide was because all of a sudden the transatlantic telephone cables were cut at some time. And so that identifies the timing of when this turbidity current actually hit the cables and broke them. And it raised tides. The effect of a tsunami radiating away from this, a very small one in this particular case, but nonetheless the effects of negative buoyancy, if you like, sediments which are denser than water, you mobilize them, they sink further down the ocean's continental shelf, and as a result of that change in volume, they create a tsunami-like disturbance in the same way as we talked about that an earthquake can do it. So that's kind of where we plan to go today, is we'll use what we know about our understanding of pressures on structures to be able to understand a little bit about these systems that we're looking at here. Okay? So let's see how this works for us. So how do we start this off? Let's, as we usually do, summarize things, but summarize things slightly differently. Summarize things by talking about buoyancy. And so buoyancy is relatively a straightforward principle. It draws on all the stuff that we've done before, all of these points that we've dealt with before. And so the easiest way to look at buoyancy is to kind of consider this little control volume we have that's present underneath some water. And so if we take this little cube, as we've done in the past, that has some kind of area attached to it, which is this top surface, has some, let's call it a height attached to it, which we'll call h, has it's some depth below the water surface, which we'll call y, as we've tended to do. And we can do a force diagram to think about what the, for instance, the pressures would be acting on this. So the pressure acting on this top surface is going to be equal to the unit weight of the fluid times y. As we go further down, we know that the pressure at the bottom is going to be equal to the unit weight of the fluid times y plus the change in height. We know all this. And so in other words, we know that we'll have a pressure acting on this little cube which acts downwards here and which acts upwards here. Maybe we can call them pressures 2 and 1 or upper and lower, it doesn't really matter. So we can identify the difference between them. And we can think of what the net force is that's acting upwards, which we'll call a buoyant force. And we can think about the weight of this cube, which we've cut out of the fluid with these some magical way that the fluid hasn't come in on us, maybe with a thin membrane, acting downwards. And so that's the force diagram that we know. So what else do we know? We know that the fluid acting at a point acts the same in all directions, and so clearly the fluid acting on the top surface here is the same as this magnitude that acts horizontally. Likewise here. So what we could do is we can do a force balance and resolve forces acting upwards, the buoyant force. And the buoyant force is going to be equal to acting upwards. The forces acting downwards are going to be P1 minus P2. So this is up, this is down, and I suppose also equal to the weight of this. Let's ignore the weight. And so quite simply we can substitute for these as the individual components. P1 is equal to unit weight of the fluid times Y. P2 is equal to the unit weight of the fluid times Y plus H. Oh, sorry. You didn't stop me. These are forces, so we have to multiply fluid pressure by an area, the area of this top surface. And so this is, let me write the A here at the end of it, plus W. We'll keep W there for now. And so if we start cancelling things, we have a Y here we can get rid of and a Y here. And we're left with the buoyant force is just equal to the unit weight times the height times the area, this little cube. Of course, this is the volume of this block, and plus the weight. And so that's what you know already, right? We're including now the weight. The weight could be the weight that's in here. If we assume, as is usually done, you see here, Archimedes' principle, we assume that the weight, and we're only looking at the buoyant force, if this zone is completely evacuated, the weight, of course, is going to be equal to the volume multiplied by the unit weight of the cube. And so if we set this unit weight to be 0, in other words, if it's empty, then we just have the buoyant force is equal to unit weight of the fluid, importantly, times the volume. So I'm guessing you've seen that in your past. And so we could have plus W. So if W is empty, then this is usually how we define the buoyant force, which is just the difference between the displaced fluid, the volume of displaced fluid gives us the magnitude of that. If the fluid is equal to water, or sorry, if the cutout volume is equal to the unit weight is equal to the fluid, it's neutrally buoyant. So it doesn't circulate, it just sits there, it's happy to do it. If it's lighter, then there's a net force upwards. If it's denser, there's a net force downwards. And so from that, the out of balance forces mean that it's mobile. So all we're doing here is we're mobilizing what we know about these systems, right? So we've done our three things that we've talked about. We've calculated the forces that are acting on a plane from the depth of the centroid of this face, unit weight times the area of this face, and likewise for the other faces. We haven't needed to do this because we've only resolved vertically. We haven't resolved horizontally because we don't need to. We know that this triangular distribution on the side, or prismatic distribution on the side, is the same as on the other side, so they directly balance each other. And so we don't need to resolve horizontally. And there should be no net moment that's involved in this as well. And because we were only resolving vertically, we haven't explicitly calculated where this force acts, but we know that on this plane here, it would act at the centroid, which is just our central point of this surface. So we know it acts, and the one on the bottom acts in the same thing. So there's no net couple to rotate it. And so there is no real failure mode in this. But if there is, this cube is taken out and has no mass in it, then there would be a net force. And of course, the failure mechanism, the third thing that we'd look at, would be which direction does the out of balance force act. If W is equal to 0, then the net buoyant force will be upwards. in the direction that we've defined as FB. If the unit weight of the container is greater than the liquid, the fluid around it, then it will net sink. And so so that's kind of the three things. So how big is the force? Where does it act? And what is the failure mode to do that? So it epitomizes the things we've talked about. Okay. So last time we talked about forces on plane structures. This time we'll talk about curved structures, and then we'll talk about buoyancy afterwards. So that's our plan, I think, for today. No, I think that is our plan for today. Okay. So just quickly through some examples. I won't go through laboriously to identify every single component, but I'll just try and make the cases for the kinds of things that you should look out for in these. So this is a bit of a contrived example. It's a culvert or a pipe that's half filled. It's asking where the net reaction is if you cut this thing in half. I say it's a contrived example because why should we care about that? No, we don't really. The net resultant, if you don't cut it in half, is going to be just the weight multiplied by this, the unit weight of this multiplied by its area or volume, and that's going to have to be countered by the force acting upwards if it was a whole pipe. But if it's a half pipe, then we do that just because it's a preparation, if you like, for being able to do something else. And that is that we can look at it by taking this structure and just cutting it in half and drawing a free body diagram that represents this thing. So the free body diagram will look something like this. Do you want to do it larger? Okay. And if we isolate this free body diagram, we have to put some forces on that allow it to stay in place. Forces first due to the fluid, which would be on the left-hand side. So we're used to drawing things like this. Forces due to the weight, which would be just the, what would the weight be? The weight would be equal to the area times the length times the unit weight of the fluid. And so those are the forces due to the fluid. And they have to be acted on by what's pushing back from the wall of this ring as a horizontal force and a vertical force, which we don't know. And so what we can do is we can try and calculate what those reactions are if we know what the other forces are. We only have one force acting horizontally, so F1 and FH have to balance. We only have two forces acting against each other vertically, and so these have to balance. And so if we can calculate what F1 is, and if we can calculate what the weight is, which we have done, we can figure out immediately what the vertical component of force is. And we can also do the same to calculate FH. What's FH? FH has to be what? Unit weight, area, times depth of the centroid. Unit weight of the fluid, it's water, it's in English units, so it's 62.4 pounds per cubic feet. The area is going to be 3 times 1. Is it 1 foot into the... Yeah, 1 foot. Okay. 3 times 1. And the depth of the centroid is what? It's not the point where the fluid pressure acts, but it's the side of this. The centroid is of this surface is this. So the middle point. So it's going to be halfway down. So it's going to be at the location, so the magnitude is going to be 1.5. And so that's the calculation for that. Yeah, okay. So you have all those. So that's all done. So now if we have that, where does that force act? How do we rationalize that? Well, certainly we know that the forces, all the pressures acting on this surface have to act perpendicular to this surface. And so from that we can surmise if you extend these vertically upwards, we know that all of these incremental pieces of force that are looking backwards have to act through this origin. And so we know, although I'm completely obscuring it, that they all have to act through this point, just by the geometry of the system. And if we want to know what the inclination of these forces are, then we can do that by looking at the force acting horizontally, the force acting vertically. I guess I've drawn them differently around. These are the other way around from these, so these are acting in the opposite directions from these, doesn't matter. And so we can calculate if we want this angle at which they would act, and we can also calculate the magnitude of the resultant just from Pythagoras, right? Nothing more than that. So we're doing two things. We're calculating how big, what the magnitude of FR is in terms of its size, in terms of newtons or pounds in this particular case, and we can also calculate the angle it acts if we want. And so that's all documented in the bottom part. So as I say, a little contrived, because why would we want to split in half? If we wanted to calculate what the reaction really is, it's just a vertical reaction against the weight of it, because everything else balances out on other sides, right? You can imagine that we could do this calculation for the other half of this, flipped over, and it would be exactly the opposite. And so there's no net lateral component because everything balances, and the only net vertical component is the weight of the fluid acting against the reaction from the base of the pipe. Okay. So the final calculation for that is this. And so the reason for doing that maybe is an entree into this, to understand how we might calculate, for instance, what the force is that's acting on this perhaps more interesting structure. And so that's basically, we can take the analysis that we've done already and see what we have to add. So how does this differ from the previous example? The only thing that's really different in this is that now this little isolated free body that we have has an extra pressure that's acting on this surface, which would be our component here. And when we look at the magnitude that we have acting here, since this pressure is acting vertically downwards here, we have a pressure magnitude of the same magnitude that's acting here, which we can draw like this. But in addition, this kind of linear change with depth. And so it's useful to be able to think about what this looks like. And so now when we do the free body, we have the horizontal force which is acting, which we had before, but it doesn't look quite the same as we had before. Right? If I drew this, right, because this is a free surface, this is atmospheric pressure. We'll take atmospheric pressure as 0. In this case, atmospheric pressure would act here, and so if we drew this up, actually it's not a bad, I'm probably going to complicate this diagram by doing it, but if we draw this up to the surface like this, it's not quite continuous. This should be a continuous line that goes down through this. And so we're taking a part which is this prism, which we won't use, but you just have to realize that this is the force that's acting. And so this length, this pressure here, has to be the same as this pressure in terms of this distribution. So all that's changing now is that this force will be different from before because it's bigger, and we have an extra force acting downwards that we can add into this. So now we can do the same things in terms of resolving horizontally and vertically. If we resolve horizontally, this force has to be countered by this, hence these two. And so if we can figure out exactly what this one is, then we can calculate what FH is. And likewise, these forces all have to be the same. So F1 and the weight act in the same direction, and FV acts opposite to that. And so summing those, we end up with those two. And so in the same way, what would we have? This is pretty easy for us to get, right? It's just a volume multiplied by the unit weight of the fluid. This is pretty easy to get because we know that it's going to be the depth of this point here multiplied by the area of this plate times the unit weight above it. And the one we don't have is going to be the vertical reaction. And so if we do those, we can calculate those. So in other words, we can get this quite easily. So this is going to be, well, I don't need to belabor the point, right? So poor choice of terminology, right? I think here. This shouldn't maybe be, this is the depth of point C, not the depth of the centroid. So the depth of the centroid on this is going to be equal to whatever this component is. this is uppercase C. HC equals, yeah, this is equal to HC, I guess. HC for force 2. So I won't go through it. I think I'm over explaining things maybe. So we can get the magnitudes of the force acting here. We get the magnitudes of the force acting here, and we have everything we need. We want to calculate the inclination of the resultant. Since we now have both FH and FV, we can get the magnitude of the resultant. And since we know the point of action of all of those forces, we could take moments around arbitrary locations and figure out exactly where the absolute point of action is as well. You could estimate exactly its location. So I won't do that final part. And of course, one of the reasons for having curved surfaces, not so much on airplanes, I guess you have it on gas tanks, pressurized gas tanks, airplanes, you have curved surfaces so you don't have stress concentrations in the structure at a particular point. But one of the reasons for having curved surfaces in something like a tainter gate is this whole idea that as you have this gate that you lower to be able to shut off a sluice, so you have this curved surfaces on an arm, you raise it, water can flow underneath it, you drop it, and you cut off the water with a free surface on top of it. This is actually one near the Bay of Fundy, as it turns out. Not a very good Xerox picture of it. But the reason for a tainter gate is that you can make them very lightweight with a very thin covering of steel, of metal in this particular case, because the pressures that are acting on it all act through this fulcrum, and therefore you can design this with relatively sparse, lightweight materials and don't have to have a huge infrastructure to be able to lift it. And so this is all based on the fact that if this is a circular arc, everything acts through the center of this, and therefore you don't have to provide a large physical structure to be able to resist it. Okay. I won't do that. I won't do that. Do this. Okay. So this is interesting. So a bit more interesting than you'd think. So this is the idea of having a not a ball, but I guess obviously it has to float. It has to be. We could say something about the buoyancy, but let's not worry about that quite yet. So here's a question to be able to figure out exactly. You have this long cylinder. It's obviously buoyant. It floats in oil and rests against the wall. I guess it's a lot of oil. It's kind of a big structure for that. 3 feet in radius, 6 feet in diameter. And so the question is, what's the force that acts on the wall? What's this? So again, what's the force that's acting horizontally? And so we can use exactly the same things as before. We can recognize what we do and don't know about this. What the easiest thing to do is probably to isolate this into a free body that looks like this. If we do that, then we can mark all the forces which are acting on this. What would they be? We have a force that's acting on this side, which would be this. It comes from the surface, so it would be this pressure distribution that is 0 at the surface and unit weight times depth at the bottom. So that's the first part. So we'd have that acting here. We'd have something acting here as well. But of course we have to think about exactly what this could be. We could think that it might look like this because it's going down from the surface. But of course we know that the other thing we know is this. This is a pressure. We know that as we go horizontally in a fluid, the pressure can't change. And so if we can move from this point here through the fluid, and I guess I will draw it. So if we can move from this point here to this point here, which is at the same height, these should be at the same pressures by definition, right? Seems kind of strange that that's the case, but that has to be the case. This pressure here has to be exactly the same as this. So the actual pressure at this point has to be some magnitude this, and then and also by the same token, the pressure at this point has to be the same pressure at this point because they're both at the same elevations. And so the magnitude of this pressure here has to be the same as this. These have to be equivalent to each other. And so if that's the case, then the distribution has to be not just this triangular distribution, but a triangular distribution plus a prism that's tacked on the side. You know, we could have drawn this. The alternative way to draw this, I guess, would be to draw it like, yeah, I will draw it. So we could also draw it like this, right? As a prism like this with a triangle tacked onto it. Perhaps that's easier to think of. But the end result is that these are the same. This length here has to be exactly the same as this length here. And so if we know that, then it's relatively straightforward to calculate. What else? We're only interested in the horizontal force. So we don't have to worry about the fact that this has a certain amount of weight that's acting downwards, and this has a certain amount of weight acting downwards, and this has a certain amount of weight acting downwards, and this has a fluid pressure acting upwards, because we don't have to resolve vertically. If we did have to say, that's really a buoyancy problem, so we won't have to do that. So I'll get rid of that. And so we're just resolving horizontally. So I'll just get rid of those. Right? So remember that you have to, if you had to resolve vertically, you'd have to do that. And so the rest is just balancing forces. We would like to know what this is. We think we can know what this is, and we think we can know what this is. So F1 is going to be what? We can just write it out. F1 is going to be the unit weight times the depth of the centroid times the area. It says 9 feet long, so this is going to be 9 feet into the page, and so this is going to be 9. We know that this is equal to 6, I guess, right? So unit weight, the depth of the centroid is 6 over 2. The area is going to be 9 times 6. Feet, I guess, in this particular case. Feet squared. So F1. If we want to do this one, what would the calculation be? I guess you have to be careful, right? Because you can't get it directly from just using the depth of the centroid. You'd have to add a pressure to it. And so I guess you could still use the mean pressure. So I guess for F2, what would we want to do? F2, we know that the pressure distribution is going to look like this. And so probably the easiest way to do it is to take the halfway point, where we take basically this triangle here. Sorry. We take this triangle here and add it on here. So in other words, what we can do is we can take the area of that part times the mean pressure, the average pressure, and what's the mean pressure going to be? It's going to be equal to the mid-height of this, the midpoint. And so it's going to be equal to the area multiplied by the unit weight times H average. And I think H average is going to be 3 feet down, and it's halfway down this. So this height is going to be 3 feet plus 3 feet over 2 feet. So we have this, we have unit weight, and we have an area. The area is going to be what? It's going to be equal to the height of this, which is the radius, which is 3 feet, multiplied by 9 feet. And hopefully that's the calculation that we get from these. Yeah.
Where's the 9 come from?
9 is into the page. It's in the problem statement.
Oh.
Yeah, so, 9 feet long. So, yeah, so it's just into the page. Okay? Yes? This one?
Yeah.
Okay, so we know the key information is that we know that the pressure at this point, we think it might be atmospheric because it hits here, but it can't be. This thing is pushing against it. We know that if we go from this point here all the way here, the pressure here has to be the same as this. We know that at the bottom of this, the pressure has to be the same as this. And so the distribution of pressure, if we draw it out, is going to be, draw it the other way around. We know that this pressure here is going to be equal to the unit weight of water times its depth on this side, and so the depth is 3 feet. Oops. This is going to be, pressure is equal to the unit weight multiplied by 6 feet. And so what I'm doing is, the easiest thing to think about is if I draw a straight line down here, and I take, if I draw, forget that. If I take the middle point of this, and I draw a straight line down here, I can take this little triangle here, and I can plant it right here. And if I do that, then I know that the pressure acting here is this prismatic distribution, which is just equal to the depth at half height. And so the pressure at the middle is going to be equal to 3 feet. This whole height is 3 feet. And so this height is 1.5 feet. And so the pressure here is equal to unit weight times 3 feet plus 3 over 2. Okay? And so if I know the pressure at this point, and I know it's just a uniform distribution, then all I'm doing is I'm taking it and I'm multiplying it by this height times 9 feet. Because the area A is equal to 3 feet times 9 feet. So that's it. So so two things. Pressure here has to be the same as this point here. Pressure here has to be the same as this point here. I guess 3 things. And also that we can do this little trip of cutting this linear distribution off here and putting this triangle up above it to make it simplest. And actually kind of it's the same thing that we've said before. If you remember, we've always defined that this resultant force is equal to the unit weight times the area times the depth of the centroid of that plate. And I guess we could have used that, right? The depth of the centroid of this plate, yeah, I guess I maybe making it more complicated. The depth of the centroid of this distribution is here. But I guess if you do that, you have to remember that the free surface is up here and not this point here. And so the depth of the centroid, if I rewrite this as the area times the unit weight times hc, this is just the average pressure that's acting on the plate. Right? We've said that. Wherever this plate is, free surface, plate, wherever you like, the total force that's acting on this is the average pressure that acts on this plate, which is at the centroid, multiplied by the area of this plate. And so all we're doing is we're accounting for the fact that the average pressure on this side is not the distribution of this triangle, but it's the distribution of this prism. Okay? All right, so let's leave that. I'll let you go through this, but I think this is useful because this basically is an example that's used to show the commonality of all the methods of solving the problems that we're dealing with. It's a very simple problem. It's a little contrived, but it's a gate which is sloping at it's a depth of 1 meter. It has liquid behind it. I guess it's something a little bit denser than water, but just to make it easy. And the question is, what is the force that's acting on this plate? And it uses 3 different approaches which give, of course, exactly the same result. One is to use our approach with the depth of centroid and our second moment of area approach, where this is the gate that we have here. And if you use that, we get the force that's acting from the depth of the centroid, the area, and the unit weight. And we get the location where it acts from the parallel axis theorem. And you can go through the calculations for that. The second approach is to use the idea of a pressure prism that's acting on this. We could draw the pressures that act on this surface. And if we do that, we know that it acts 2/3 of the way along it. And we can calculate, again, the magnitude of the force from the area over which the force acts and the average pressure. This is what we've called P over bar. So in other words, if you take this distribution and do exactly what we did in the previous example and go at half height, take this here and take this part here and subtract off this and add it on here, then the distribution is just a linear distribution, and to calculate the magnitude of the force, we just use the average pressure at this point. And we know that YR for this triangular distribution has to act 2/3 away from the top from what we've done. And if you do that, when you calculate the location where this acts, in each case it comes out to be the same numerical value, just stated in this kind of slightly mathematical way, but just to show it's the same. And the final way is the way that we've done these last examples, which gets to be more complicated, but it's the same idea. We have a gate, which is here, which I should, whoops, this gate here. We can draw a free body that isolates a block of fluid in the system, and we can do a free body to look at the distributions here. Looks horrible, but it ends up being somewhat straightforward. If you take resolving horizontally first, we know that the horizontal force that's acting on the gate, has to equal this force. This force, of course, we can calculate pretty straightforwardly. It's just 1 meter times the components. And so we can calculate what this is as a result of knowing this. If we resolve vertically, then we have a vertical force acting here, weight, and a vertical reaction acting upwards. So this we can calculate, this we can calculate, but this we can't calculate so very easily. And so we can just write a balance diagram that this force acting upwards has to equal this and this together, which is just this expression here. This we can calculate, this we can calculate, and this we can get from knowing that. And then if we have those two components, both the vertical force, both the vertical force and the horizontal force, we can use Pythagoras to be able to calculate the resultant, which comes out to be the same as the one calculated up here. And if we want to know where it acts, we can assume that it works 2/3 of the way down here, and we can take moments around that point to be able to show that that's true just by taking moments. So 3 different ways. They should, obviously, since it's the same physical system, they should be absolutely equivalent. And so I won't go through this now. If you want to, when we go through our review session for the midterm, I might do it. Out of 3 topics we've done, there's almost certainly to be a forces applied on a structure question just because of the distribution of course material, right? So have a look at that in your own time and see that you can understand the things that we've done. Okay? All right, let's quickly talk about buoyancy. So buoyancy we introduced earlier on as being able to calculate exactly what this buoyant force was. It really relies only on the things that we've talked about so far, and that is we can calculate from Archimedes what the buoyant force is that we apply to a structure, and we can understand a couple of things about it. Again, if we know what all the forces are that are acting on the structure, we can also define some kind of failure or displacement mode, and we can resolve to be able to do things like calculate tensions in a cable. So we don't need to do this. Go straight to maybe an example. So you have a buoy or a buoy that's in the water. Sometimes it's easier if it's completely submerged because we know the volume isn't a function of where the free surface is. It's the displaced volume, of course, that we're talking about in terms of Archimedes' principle. And if we wanted to understand what the tension in this cable was, then we can just draw another free body diagram that includes the idea of this buoy or buoy. It has a buoyant force acting upwards. It has some weight of the buoy acting downwards, and we draw a tension acting downwards just to pull it down. So in other words, we isolate the free body just by drawing something around it, and this is the force that we have to apply on the bottom to be able to keep this in check. The reason for buoyancy is because we have these pressures acting all around it. The pressure acting on the top is less than the pressure acting on the bottom, and so there's a net buoyant force. It's the same, the net buoyant force is the same as what we've calculated before, which is just going to be equal to the unit weight of the fluid displaced times the displaced volume. And so if we resolve vertically, we have acting downwards the weight and the tension, and we have acting upwards the buoyancy. And if we want to calculate this, we know everything. We know the volume of the buoy. We know the unit weight of the displaced fluid. This is the displaced fluid, not the air that's inside it. It's the displaced fluid on the outside. And we know the weight of this buoy, and we can calculate what the tension is from that. So you all can handle that based on the more difficult things that we've done. And so we're doing the same things. What is the forces acting on the structure? The buoyant force is due to the imbalance of the vertical forces acting downwards due to pressure being less than the vertical forces upwards acting due to pressure, this concept here. The resultant we don't care about because what we said is before the horizontal forces balance each other exactly. We could show that, but we did it for this little cube. You could also show it for this sphere if you so wished, but we don't need to. And when we resolve some failure mode, we have to choose some way to resolve that. So we have the only forces that are not imbalanced are acting vertically, and so we just resolve vertically to be able to do that. And so that's our system. And so again, it uses the idea of what we've talked about. There's also this interesting idea of stability. And so in the same way as we talked about forces on structures, how big is the force? Well, we calculate the buoyant force. The next question was, where does the force act? Of course, it's important for us to understand where the force acts in some circumstances. And so it might be worth us mentioning, I guess it's written here. So the magnitude of the force is due to the unit weight of displaced fluid times the volume. The location where it acts is at the centroid of the body. So in other words, the location where it acts is if you imagine it as being a uniformly dense body, maybe of zero density, the centroid of that would be the same as the middle of this plate. So if it was a cube, it would be at the center of the cube. So the centroid of the physical body. And the reason that that's important is because sometimes we're interested in stability of structures, capsizing boats or capsizing cruise ships even more tragically. And so the idea is that it's quite easy to do for submerged bodies. I'll just look at, yeah. And that is that if you look at a submerged body, the buoyant force always acts at the centroid of that volume. And so for a submerged body, it'll always be the same location. Even if you twist it, move it, turn it upside down, depending on the distribution of the weight inside that, then the center of gravity of that would be at the distribution of that internal weight of the structure. And so tragically, as you know, this past, was it in the summer or was it in the spring, the Korean cruise ship, ferry, going off to this offshore island with a whole school basically on board, a whole grade of one big high school on board, didn't have the cargo fixed, the boat rocks, the cargo moves, all of a sudden the center of gravity has changed. And as a result of that, sometimes it becomes unstable. So if the center of gravity is below the center of buoyancy, so this is the center of buoyancy, all is good. If like having a piece of cork with a tack in the bottom. The cork will always bob up. If you turn the cork upside down with the cork with the tack on the top, it'll fall over and it'll find its new position. A bit more complicated because there's a free surface involved, but it's the same idea. If the buoyant force, the center of buoyancy, is always above the center of gravity, then the net couple in this case, if you resolve moments, is to do this. And so it will always turn this center of buoyancy so it's above the center of gravity and it's self-righting. If it's the other way around, of course, the center of gravity is above the center of buoyancy, then you only need a small misplacement to one side, and now this net couple, this goes down, this goes up. You can calculate what the moment is. The moment's out of balance with everything else, and it has an unresisted, if you like, overturning couple. And so in the cases where the center of gravity is above the center of buoyancy, intrinsically it's unstable. It only needs a small tilt to one side to make it fall over, like balancing a cork in fluid to be able to do that. So that's something that we need to know. The easiest exposition of that, I suppose, is to, one easy way to think about this is for things on surface, which are more complicated. And the more complicated things with bodies that float on the surface is that the center of gravity will always be in the same place. Just the distribution of cargo within the ship. And so if you imagine taking that ship and finding the balance point, if you could magically put it around a point on your finger where it would just hang in space and not move, that's the center of gravity of the ship. But the center of buoyancy will change as a function of the fluid that's displaced. And so this center of buoyancy, when the ship sits like this, might be here, and it would almost be from doing this if it was a cube, right? That's the center of buoyancy, is the centroid of that volume. If the ship lists to some side, then the center of gravity won't move. It'll still be in the same physical location, but this will be moved now because this shape of displaced fluid has now changed, and it's going to be the centroid of this new shape. And so what you'd like, again, in this more complicated case where you have a free surface where the boat's flopping around, is that you'd like that the center of gravity sits above the center of buoyancy, so there's a restoring couple that puts it back. If the converse is the case, that the center of gravity is sitting above it and the center of buoyancy is here, then you can see that in this particular case you have a net couple where this is acting downwards, this is acting upwards, and as a result there's an overturning couple, and you know what the ultimate result is going to be. It's ultimately going to come to rest where this top part here is this part here, center of gravity is here, and the center of buoyancy maybe is above it. And so always remember the case of that. 2 more seconds just so we can finish this up. So we can do some other examples. And you can work through this final one, 2.95, if you so wish. The idea is, we've said that buoyancy only is ever equal to the unit weight of the fluid multiplied by the volume that's displaced. So if you take, for instance, now a very simple system where you have a cap placed on a pressurized tank that has air above it and that has a block in it which is keeping this cap closed. The question is, what pressure do you have to apply to be able to just physically blow this off? And so the question is, how does adding a fluid pressure to this surface influence the buoyancy of this? Well, we know that the force of this, the buoyant force due to this, has to be equal to the unit weight times the displaced volume. The volume of the fluid doesn't change as you change this pressure, and so the buoyant force of this won't change either. What's the reason for that? Well, the reason for that is if you look at the pressure distribution that you have on this particular block, initially the pressure distribution might look like this. Right? And so this pressure at the bottom is the same pressure that's acting upwards, and this pressure at the top is the same pressure that's acting downwards. And so really the buoyant force is due to this mismatch in forces here. If you add an extra pressure to the top, all you do is you physically add an extra amount due to this, due to the fact that you're adding a fluid pressure to the top. And now the mismatch between pressures top and bottom is now this mismatch, which is the same as this. And so the reason that the buoyant force doesn't change as you pressurize is basically because if you increase the pressure at the top by 10 megapascals, you also increase the pressure at the bottom by 10 megapascals, and it's the difference between top and bottom pressures which is giving you this expression. And so the free body diagram that basically solves this problem is a pressure that's acting upwards, which becomes larger as you increase this pressure. The pressure acting downwards on the fluid has no influence on the free body of the weight of this concrete block and the buoyancy of the concrete block which acts against it, and therefore you can solve for this. If you solve for pressure, you can solve for delta H. Okay. So that's it. We've run over slightly. So we finished talking about forces on structures, which predicated on forces at a point. We talked about buoyancy. And now I think you have all the stuff you need for the third assignment to be live.